Hello. I want to go over this language that I recently found and I've been working on for a little bit, and it's called Cuda, and it's made by NVIDIA, and it involves based on what I've learned, a lot of matrix operations, so addition, subtraction, division, elemental matrix stuff, and then matrix the dot product of matrices, a whole bunch of stuff. I've only really touched the surface of it because I'm still learning it. But I wanted to go over a video that involves using CUDA to do matrix addition, elemental matrix addition. So with CUDA is we have a big grid is what we call it. So imagine just one big box, and within these boxes, within this one big box, we have something called blocks, which are just mini boxes within the big box. Um, and within these mini boxes, we have something called threads. Um, and you can define how many threads are within each block. And each of these threads is doing a single operation for the matrix, right? So you give it, so you say matrix A plus matrix B at 0, 0 on thread 0. Just that single thread is going to do that single operation. And what this does is it allows you to do all of these single operations in one time in parallel when compared to the CPU. Um, if you say, I want to add 100 elements together, you would have to do each addition problem step by step, one by one, which if we say it takes 100 seconds to do 100 operations, it would take you 100 seconds. While on the GPU, you can do all of these 100 operations in 1 second. So it makes it faster to do, these operations. So starting off, we're going to do declare a kernel, which is going to allow us to use the GPU to do the um, addition. So we're going to call it global. Global is how we define the this function, the addition function within uh for the GPU. Um, void add with kernel. So kernel is what we call it, right? This is called a kernel for the GPU. So then we pass an int matrix A, int matrix B, int pointer result matrix, and then the int rows, int columns of the matrix. So this is going to be done. So I'm going to do an example of a 5 by 5 matrix. So both matrix A and B are going to be a 5 by 5 matrix with 25 elements within, and result matrix is also going to be a 5 by 5 matrix with 25 elements within. So within here, we're going to declare a row variable. So row int row is equal to block idx dot y. So what does is within our big grid, this is saying come to the block index at the current y. The current yeah, on the y-axis, the current block on the current y-axis times block dim dot y. Block dim is usually represented as the, I believe, which one is it? The amount of threads within a block. Yes, the amount of threads within a block. So here we would say come to, if we're starting at block index 0, so 0 on the y-axis, and we have four threads within this block, we would do 0 times 4, which means, 0, and then plus the current um, thread index, index dot y. So if we're starting, from the very beginning of an iteration, all of these would be 0. So block index y 0, block dim y would be 0, and then thread index dot y would be 0. So this means go to the row 0, right? And then in column, we do the same. Block index dot x this time, idx dot x times block dim dot x plus thread index dot x. Okay, now we're going to use an if statement. So if we want to keep adding uh, um we want to keep adding um if the rows are within these bounds, right? So if row um if row is less than rows and column is less than columns. So this is saying if this current row is less than the amount of rows that we have here, and this um, current column is less than the columns we have here, proceed, right? Um, so here we're going to say result matrix, and I'll go over on my iPad how exactly this is working, right? So result matrix at the current row. So at the current like I said, we have one big grid, which is the box, um, the big box, and then the mini boxes. So this is calculating the mini boxes row and column. So the current row times the columns we have here. Oh, this should be sorry, columns. Um, plus the current column we're at within the boxes, right? Is equal to matrix A, and we would just copy this because we're doing the same thing. Matrix A at the same position plus matrix B, which is supposed to be at the same position as well. Uh-oh, what did I do? I didn't mean to do something. I ran it by accident. Sorry. And then paste this here. So essentially, this is pretty much it for our kernel. Um, this is going to do the additions, the matrix addition when we call it down below, which I'm gonna show you in a bit. Next, I want to make a little function that checks for errors when I call it um, when I call this function. It's just going to check for errors to see if anything is wrong. So we're just going to call it we're going to call it Cuda check for errors, and it's going to be of type Cuda error. So Cuda error underscore T. To be honest, I'm not quite sure what this is, but I know that it's it checks errors. Um, we're going to call it check status. So check the status if it's wrong or not. Um, and then here we're going to say another call in another CUDA error underscore T. And we're going to call this CUDA status. Uh-oh. Status. And then we're going to want to display a message. So const cd string message, right? So here we're going to say we want an if statement. So if the CUDA status that we have for down below, and I'm explaining this more in depth in a bit, status does not equal CUDA success. So this means the code was executed fine. So if it doesn't execute fine, we're going to throw a error message. So we're just say CUDA error and then display the message that we're gonna input um, message and then do a little space, and then use something called Cuda, get error as a string, um, and then pass in the Cuda status. So this is going to grab whatever the CUDA status was and just turn it into a string so we can read it. And then exit failure because code didn't work. And then return CUDA status. So this is just going to check for any errors within our code. And then now we want to define um, another CUDA error key, which is going to calculate our we can call it within the main, and then we can call this within that function, this global kernel within that function as well. So CUDA error key add with CUDA. Just going to call it add with CUDA. And then here, essentially, it's going to take all the same parameters as we have here for the kernel, and we're going to do the addition within here. We're going to define all the variables. We're going to allocate the memory for the matrices, um, and so on and so forth. So we're just going to do this for now. And next, I want to do a print matrix function real quick. So print matrix. We're going to pass in the int matrix, int rows, int columns, and then on std string reference it name. So name of the matrix for std out name, and then for int row is equal to 0, while row is less than rows plus row, and then for int column is equal to 0, column is less than columns plus column, std out the matrix we pass in matrix at array row times columns plus column, and then a space, std out std and l. So end line once we finish the current row, std out std and l. So this is just end line or a line for once we finish printing the whole matrix. This is per row, and then this is per matrix. So end line per the matrix. Okay, int main. Here we're going to declare our rows. So int rows is equal to 5. Int columns is equal to 5 as well. And then we're going to say int elements in matrix is equal to rows times columns. Why are you? Oh, right. So then we're going to define our matrices. So pointer matrix A is equal to a new int of size, new int array of size elements in matrix, right? And then we're going to do this for B as well, matrix B, and then the result matrix. And now we want to initialize our matrix A and B. So we're just going to say a little simple for loop for int I is equal to 0. I is less than elements within the matrix plus I. And then matrix A at the current I is equal to um I times or I plus 1, and then matrix B at array I is equal to I times 2. So this is matrix A is going to be 1 through 25, and then matrix B is going to be like 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, so on and so forth. Um, so let's print the matrix real quick. Matrix A followed by the rows and the columns, followed by matrix A, the name. Let's copy this for matrix B. Oh, I ran it by accident. Matrix B. If I save this and I run it, it should just print out the matrix A and B. So yeah, here we go. Uh, 1 through 25 and then 0 through 48. Um, okay. So now we've done initialized both matrices. Now let's dive down into the adding with the Cuda portion. So we call in add with Cuda again, copy these parameters. Okay, here within this function, we want to create device pointers. So essentially what we're going to do is we're going to pass in the information from the CPU that is within matrix A, B, and C, or A, B, and result matrix, and pass them onto our GPU. So in order to do this, we have to declare int dev matrix A. So this means pointer device matrix A. Set this to null pointer. And then we're going to do the same for B in the result matrix. Result matrix. There we go. Why is this wrong? I forgot to add um the variable type. Um so we just copy and paste it. There we go. So Cuda arity add with Cuda, and then there we go. Okay. So device pointers for both A, B, and the result matrix, right? And then now we want the elements again. So elements in matrix is equal to rows times columns. Okay, sweet. So now what we want to do is we want to allocate the memory from the main to our device GPU. So in order to do this, we're going to use something called CUDA CUDA malloc, which means CUDA memory allocation. So we're going to allocate the memory that we placed for A and B here into our device, our device, our GPU, right? So we're going to call in the check status function first, check status, and then within this um, function, we're going to call in the uh, CUDA malloc, CUDA malloc, CUDA memory allocation. And now we want to reference our current dev matrix. So reference the matrix A, and then we want it to be of size elements times size of int. So this is right here. So we're going to allocate the memory of, because remember of this is just a null pointer matrix, right? And then we're going to allocate enough memory for whatever elements in matrix is, in this case 25, and then make it be the size of the of integer. because that's what we're using to add, right? And then here we're just gonna put a message, um, just couldn't allocate memory for dev matrix A. So this is in case it doesn't work, we're gonna see this message, right? And then we're going to do the same for matrix B, and then result matrix. Just change these to B, result matrix. Sweet. So now after we're done with this, we want to copy now. So we've allocated the space that we need for um, all three matrices, so matrix A, B, and the result matrix onto the GPU. So this means we have all the space needed for the GPU to do the calculations. So now we want to copy the memory of, we want to copy the elements of from this matrix A and B from the host to the GPU. So once again, we're going to say check status, and then now we're going to use something called Cuda mem copy. Cuda mem copy. And then here, as you can see in right here, we're going to need a destination of where this memory is going to be copied to, who we're copying it from, the size of it, and then what kind of CUDA mem copy we're doing. In this case, we're going to be doing host to device, so the host CPU to the device, which would be the GPU. So here we would say dev matrix A from the matrix A. And then once again, it should be elements in matrix times size of int. And then we're going to say CUDA mem copy, CUDA mem CPY host to device. So this is saying, oh, we're going to copy the memory from the host to the device memory. And then just another message again, couldn't copy memory from matrix A to dev matrix B. And then, sorry, I need this and this. There we go. Sorry, that should say A, not B. So A and then B, and then here we're going to do the same thing for B and then B. So we only need to copy the memory for A and B because those are the only two that have information in the main. Okay, so after this, we want to create our blocks, our block size, which is the mini blocks, the threads within the mini blocks. So how many like little people within the mini blocks are doing one calculation at a time. So we're going to say dim3 block size. And since this operation won't be too big, we're just gonna typically you want to do 16 by 16. So what this means is we're going to create a 16 times 16, which is in the X and then the Y axis. Multiply those together for a total of 256 threads calculating a single operation. So what this means is that within one block, we're going to have a 16 by 16 amount of threads, 256 total. And each one of these threads is going to be doing one calculation at a time for the matrix, right? But since we're not using that much information, I'm going to make it smaller and make it a 4 by 4, which would mean 4 threads in the y-axis, x-axis, and then 4 threads in the y-axis for a total of 16 threads per block. Right. and then I need to add the semicolon. And then dim 3, we're going to say grid size now. So this is going to determine how many big grids, though, so the big boxes we're going to have. And uh, in order to calculate this, you could easily just say 3 by 3 or 3 by 4, how we did above. So we would have 3 blocks in the x-axis and then 4 blocks in the y-axis for a total of 12 blocks in total, with each block having 16. So we'd have 16 times 12, um, which is I don't even know how much that is. A lot of threads is what I'm trying to say. Um, but this means that we could have an excess of boxes, of grid sizes and block sizes as well. Um, in case our like operations aren't too big, which in this case they aren't. Or so to calculate it accordingly to the size of threads that we have, we would grab the columns, our current columns, and subtract a block size dot x minus 1. And I'm going to explain to you what this um, is really doing and how it's actually calculating. But essentially, this is just going to calculate the correct amount of grids that we need um, for our calculations. And then divided by block size um, dot x as well. So this is in charge of the x amount of blocks. And then for our y amount of blocks, we're just going to say parentheses rows minus block size dot y minus 1 divided by block size dot y. So this is going to, why is this wrong? Yeah, delete this. So this is going to create an x by y amount of grids that is correctly appropriate for however many operations we're doing. So once we have the grid and block sizes, now we can actually call in the kernel. So we're going to call in add with kernel. And then now to add with the kernel, we use 3 brackets like this. And we're going to pass in the grid size, and then block size. So this is essentially saying is I want a grid amount of grids with a block size amount of blocks within each grid, right? And now what we do is we do the parentheses and then we pass in our parameters. And in this case, we would pass in all of the parameters right here. So we're going to pass in dev A, comma, dev B, dev matrix B, comma, dev result B, right? And then just pass in the original rows and columns. Boom. There we go. Um, After this, we want to do a check status again. So check status, and we're going to call in Cuda device synchronize. I believe what this does, I'm not 100% sure, but I think this synchronizes the host CPU to the GPU, I believe. I'll look into that more. I probably should have before making this video, but that's what I think it does. Um, and then we're just gonna call in a message couldn't synchronize device. Okay, so after this, essentially we already have the resulting matrix within dev result. So now we want to copy that information back into our result matrix within the main. So in order to pass that information back in, we're going to do something similar to this, how we did here for A and B. But now instead of to the dev matrix, we're going to put the original matrix. So we're going to say check status. where do we want to send this information to? We want to send it to the original result matrix. Where do we want to copy it from? We want to copy it from the device matrix, the device result matrix. And it should be of elements, should be a size elements in matrix times the size of int. And then where do we want to copy it from? We want to say Cuda device, or sorry, Cuda mem copy device to host. So copy the information from the device to the host. And then just another message again, in case it doesn't work. Couldn't copy memory from dev result matrix to host result matrix. So just result matrix. Uh-oh. Why is this wrong? Cuda, oh, I didn't even, sorry, I didn't even call the function. Cuda, mem, copy. And it should be, is that it? There we go. That's why it wasn't working. I even called the thing. So then after this, now we are essentially done. So now we want to free up the memory within the GPU. So we're going to say check status, check status, and then we're going to pass in um, the dev matrix, dev uh, matrix A, and then a message. Oh, let's see, I'm jumping the gun. Check status and then CUDA free. So this is going to free the memory within the GPU, and then dev matrix A, and just a message of couldn't free dev matrix A, and do the same thing for B and the result matrix. Result, result matrix. And then return CUDA success. Um, in case all of this is so essentially it returns successful if all of these have been executed properly. And now after we print out these matrices, now we want to call in add with CUDA. So we want to call in this function, all of this function. And what are we going to do? We're going to pass in matrix A, matrix B, the current result matrix, which is empty, our current columns, our current rows, and our current columns. And now this means that our result matrix should have the all of the elements within. So we're just going to say print matrix, pass in the result matrix, pass in the rows, pass in the columns, result matrix for the name. Now we want to free up the memory, so delete, I think delete matrix A, delete matrix B. So we're just cleaning up here. Result matrix. So now if we run it, it should work. Uh-oh, so here we go. CUDA error couldn't copy memory from matrix A, matrix A. Okay. I noticed that there was a couple errors with my code. Starting from up here, this should say columns, so less than columns that we have here. And then with the allocation of the memory, I messed up. I'm allocating memory from the host when in reality I should be doing it for the dev matrix. So dev, and then we just got to pass in dev matrix B, and then dev result matrix. And then within here, the grid size, this should be adding, and this should be adding as well. I put minus for some reason. So now if we run it, there we go. 1, 2, 3, 4, 5, 1 to 25, 0 to 48. See, as you can see here, 0 plus sorry, 1 plus 0 is 1, 2 plus 2 is 4, so on and so forth. So yeah, this this code here did all of this addition on the GPU, and as you can see right here, it took only 2.28 seconds in order for this operation to be done. So it executed all of these in parallel at the same time. So essentially did 1 plus 0, 2 plus 2, 3 plus 4, 4 plus 6, 5 plus 8, all at the same time within a single thread. And it was outputted like that.
Okay, I'm going to be trying my best to explain the code I went over just now. So yeah, let's get to it. And I'd like to start off by showing that this is what I meant by having one big box and many boxes within. So this is going to be our grid. And then within this, we can have a set amount of blocks within the grid. And then within the blocks, we can have, you know, a set amount of threads. So 4, 4, 4, this is just an example. So each one of these blocks is going to be computing 4 things at a time for a total of 4 times, for a total of 12 blocks. 12 times 4 is what? 24, 48 threads in total, right? So this one grid can compute 48 things at a single time. So with my code, I really just want to go over add with kernel and then the add with Cuda, but just part of it, just the block size and grid size, because I think the rest is kind of self-explanatory. But if you do need some clarification, just let me know. So starting off with add with Cuda, I had something called dim 3 block size, and I had this as 16 by 16, or sorry, not 16 by 16, 4 by 4. 4 by 4. So essentially this means we're going to have 4 threads in the X and 4 threads in the Y direction per block. So it's going to look like this. So 16 threads per block. So this means that each one of these blocks that we're going to have within a grid is going to be able to compute 16 things at a single time. And then below that we had something called dim 3 grid size. And this we could have easily just said, you know, 3 by 3, how we did here. So that means we're going to have a big grid with 3 blocks in the X and 3 blocks in the Y direction. But the thing is, we sometimes, it might be either too much or too little blocks for the amount of, you know, operations that we need to do. So the way I did it made it so that we should have just enough blocks within our grid to be able to calculate whatever we want to calculate, right? So we had it as, and this is also going to have an X and a Y. So our X was columns, the columns that we have, minus block size, not side, size dot x minus 1 divided by block size dot x. So this is our x, how many blocks we're going to have in the x direction. And then for the y direction, it's the same, but we're going to be using rows. Rows minus block size dot y minus 1 divided by block size dot y. So this is going to be our y-axis. So essentially what this turns out to be is that in the code, I made columns and rows 5. So we're going to have 5 minus so this would be 5 and this would be 5 as well. And this is 4, 4, and this is 4 as well. So essentially for rows within the grid is equal to 5 minus 4, or 5 plus 4 minus 1 all over 4. So this is our columns. This is the grid size. That's the minus 1. And this is grid size in the x direction. So this turns out to be 8 over 4, which is then equal to 2. So we're going to have 2 blocks in the for the rows, and then columns. So this is essentially just x and then our y. It's essentially going to be the same as well. Plus 4 minus 1 divided by 4 equals 8 over 4 equals 2. So we're going to have one grid with 4 blocks. And within those 4 blocks, each one of those blocks is going to have 16 threads. So I'm going to draw this out because I think we're going to need it in a bit. So one big grid, essentially split into 4 blocks like this. And then within each block, 1, 2, 3, 4, 1, 2, 3, 4. Let me just copy this. There we go. So this is going to be our grid with then in turn our blocks with which have our threads within, right? So here we're going to have essentially we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 8 by 8, 64 threads. So 64 threads in total, each one being able to compute. And with my example, remember it was a 5 by 5 matrix, which is 25 elements. So not all of this is going to be used. Only, I think it's either only going to be 25 threads or 50 threads that are going to be used for our operation. Okay, so if you remember, with added with kernel, we have the matrix matrix A, matrix B, result matrix, rows, and then the columns. So this is 5, 5, 25, 25, and 25. Yeah, these are initialized. Sorry, what the heck? These two are initialized while this one is empty. So within the rows and columns, or within this function, we have int row and column. So int row is equal to block idx dot y times block dim dot y plus thread id x dot y. So essentially this row and thread is calculating the global index of the row and thread within the grid. So it's calculating these rows and these threads within the big big grid. And now for column, int column is equal to block id x dot x times block dim dot x plus thread id x dot x. So just calculating for the columns. So within our example here, oh no, not cut. Sorry. Copy. Hello, can you work? Oh my God. Paste. So essentially within, oh no. So essentially within here, we're only going to need 5 by 5. We don't need this, sorry. We're only going to need a 5 by 5 amount of threads because that's our rows. So essentially we're going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is how many threads we're going to we are going to use within the whole grid. So these other threads on the outside are they're just there. They're not being used or anything. They can be used if we have bigger rows and columns. But essentially just within the pink is what we're going to be using to calculate the to do our calculations. So let me move this out of the way. I can leave it there. So then here we have our if statement. So if row, so our global row is less than rows and column is less than columns, we will execute what's within the kernel. So this means that while row, so this row has to be less than 5. So it would only go up to 4, which would be 0, 1, 2, 3, which would be right here, sorry, 4. As you can see how many rows we have. We have 1, 2, 3, sorry, 0, 1, 2, 3, 4, right there. Because this is being 0 indexed. And then columns would also have to be 4, because column less than columns, remember we initialize this to be 5 and this to be 5 as well. This would be 5 right here, which would be out of bounds, and then this would also be 5, which would be out of bounds. But then here this would also be 0, 1, 2, 3, 4 columns. So just 5 by 5. So this is our boundary within the grid. So then after this we have our result, the actual addition part. So result matrix array, our current row, our global row, times columns plus the column. So essentially if we started off with, let's say, block index 0 times dim, which is 4. Block dim will always be the block size of x and y within here. So in this case, block dim y is equal to block size y here, so it's 4. If we change these numbers, obviously this would change as well. And then thread index 0. So this is essentially saying row 0, and if we say 0 times 4 plus 0 as well, this is row 0, column 0. So if we come to here, row 0, column 0, it's right here. So this thread index is going to be doing the first, just the first calculation. So this is also going to be here. This is going to be 0 times 5 plus 0. So remember, this is a 1D array or 1D vector, and we're just treating it as a 2D matrix. So this is going to be result matrix at position 0 is going to be is going to be equal to matrix A at array. Let me move this over. Matrix A at array row, because we want the same position as well. Row times columns plus column plus matrix B at array, the same position as well. At array row times columns plus column. So let me scoot this over. Actually, I'm going to move this over. Right? So then here within matrix A, obviously this would be 0 as well, times 0 times columns, which is 5, plus column, which is 0 as well, plus matrix at the same position, 0 times 5 plus 0, which means matrix at index 0 plus matrix B at index 0 is equal. Adding those together, we're going to put that into result matrix at index 0. So this if statement, essentially this is all being executed at the same time. All of these threads is going to be executed at the same time. So we're going to have 25 of these, of this stuff being executed at the same time. This if statement is there to keep us in bounds. Oh no. Is here to keep us in bounds. So if we say, remember that both row and column must be below 5. So if we say we had, let's say we had right here 1, this was 1 times 4 plus 1 plus 1, this would be 5. Remember, row has to be less than rows. 5 is not less than 5. 5 is 5. So this wouldn't execute, which would mean row 5 would be trying to access these threads, which aren't really computing anything. They're just empty threads. There's nothing there. Yeah. So yeah, essentially this is what is going on in the background of this Cuda code. If there's any questions, comments, or concerns, if something confused you, mind you, this took me a while to understand. It still confuses me, but I tried my best to explain. If you have any comments, questions, or concerns, just let me know, and I'll try my best to explain it to you. Yeah, thank you for watching.